Section 2 of Chapter 26 is on the topic of transformers. A transformer is a device that takes an alternating current source, voltage, and increasing or decreasing it by the process of magnetic induction. It has to be alternating voltage because it relies on changing fields producing EMFs. So let's take a look at this diagram here. We've got a diagram that shows the operation of a transformer, and it has a power supply connected to the left or primary coil. The left side has a power source connected to a coil that's wrapped around an iron core. That iron core is a large loop that goes through another secondary coil. Let's concentrate on the primary coil for the moment. Notice the primary coil has peak voltage V1 and it's alternated in time by the cosine function. So this is an alternating current source of peak value V1, peak voltage V1. And as current travels through this coil, it produces a magnetic field. Think of the coil as a solenoid, which it actually is. And the solenoid carries current. It therefore produces a magnetic field that is parallel to its axis. Since we have an alternating power source, the magnetic field also will alternate with the current in the coil. When the current in the coil is in one direction, it will produce, for example, a clockwise magnetic field. And when the current is reversed half a cycle later, it produces a counterclockwise magnetic field. That magnetic field is contained entirely within the iron core, at least ideally it is. There's always a little bit of leakage, but the iron core is able to contain all of the field lines, most of the field lines, if not all. And so the magnetic field that's produced by the left coil then travels around the core and goes through the secondary coil on the right side. So the primary coil generates a magnetic field along the axis of the secondary coil. That changing magnetic field induces an EMF around each of those loops, and that EMF is equal to the change in flux divided by the time it takes to do that. So as the magnetic field inside that core is oscillating clockwise, counterclockwise, clockwise, counterclockwise, it's inducing current in that secondary coil that is likewise positive, negative, positive, negative. And the number of turns in that secondary coil determine what the overall induced EMF is. Recall that each coil has an induced EMF delta phi over delta t, where phi is the flux through that individual coil, and then we multiply that by the number of coils because each of those coils adds the EMF up. They all add up like a string of batteries to create an overall V2. And that V2 peak voltage is going to also be modified by cosine 2 pi ft so that it's a sinusoid. Notice we have V1. We have V1 on the primary side and V2 on the secondary side. And our question then is, how can we calculate V1 and V2 knowing what we know? So here's a summary of what I just said. The secondary coil, as I said, has a load connected to it which dissipates power. The power that's produced by the primary power supply is translated to the secondary coil and dissipated in whatever we plug that into that power supply or power source. So, well, the power source being the secondary coil. Here's the symbol of a transformer that we use in electric circuits. It consists of a primary and secondary coil with number of turns N1 and N2. And so this is the symbol that we use to denote the transformer. So the question we can ask is, how is the peak voltage V2 at the secondary coil related to the voltage V1 in the primary coil? We've seen that the primary coil creates a flux through the primary coil. It creates its own flux, and according to Faraday's law, an instantaneous voltage V1 across the coil is related to the change in flux by this. V1 is equal to E1, the EMF of that coil, which is N1 delta phi over delta t. This is the value of V1 and the flux that it creates. This delta phi over delta t is then felt by coil V2, or the secondary coil. The secondary coil has EMF E2, which is going to be that same delta phi over delta t times N2. Therefore, the larger N2 is, the larger the induced voltage in that secondary coil is. Delta phi over delta t is the same in each coil. So because V1, which is N1 delta phi over delta t, is related to V2, which is N2 delta phi over delta t, because they have the same delta phi over delta t, we can cancel out the common factor of delta phi over delta t, and we can arrive at this equation right here. The voltage in the primary coil divided by the voltage in the secondary coil is equal in ratio to N1 over N2. This equation gives the ratio of the instantaneous voltages. Let's think about this for a moment. The instantaneous values of an AC voltage are proportional to both the peak and the RMS voltages. So we can write the peak voltage V2 is equal to the peak voltage V1 times the ratio N2 over N1. We can likewise say the same thing about the RMS quantities because they scale with each other. The RMS quantities are simply equal to the peak values divided by the square root of 2. So the RMS value V2 is also equal to N2 over N1 times the RMS value of V1. So the RMS voltage in coil 2 is equal to the RMS voltage in coil 1 modified by the ratio N2 over N1. Notice if N2 and N1 are equal to one another, there's no difference in the voltage. We're simply transforming the voltage in the primary coil to the voltage in the secondary coil by the process of magnetic induction. Now these equations show us that a step-up transformer is one for which N2 is greater than N1. The number of turns on the secondary coil is greater than the turns on the primary coil, while a step-down transformer is one that has the opposite. N2 is less than N1. We can also relate the currents in the secondary and primary coils by basically the same reasoning. We'll assume that our transformer is ideal, in other words, that it doesn't lose any energy. All of the magnetic field is contained within the core and there are no other losses. So, by energy conservation, the power output of the primary has to be the power that the secondary coil receives and therefore can deliver to a load, like a device that we use by plugging into the wall. So since P1 is equal to P2, that means that P1, which is V1 RMS I1 RMS, is equal to V2 RMS I2 RMS. So we can use the expressions we just did to write the current in the coils. I2, therefore, is also equal to N1 over N2 I1. I2 RMS is equal to N1 over N2 I1 RMS. Now notice the ratio of N's is reversed in this case. In the previous page, we saw that V2 was equal to N2 over N1 V1. So V2, the N2 is on the top. For I2, which we see in here, the I2, the ratio is N1 over N2. Now that's not hard to see because if the power is constant, V times I is constant. If I raise V and it's still going to be constant, that means that I has to be lowered. So a transformer that steps up the voltage also steps down the current, so that the product of the two is a constant, which is the power. So here are the expressions then for the current. I2 RMS is equal to I1 RMS times the ratio N1 over N2. A step-up transformer raises voltage but lowers current. A step-down transformer lowers voltage but raises current. So let's see how that works when we deliver power from a power plant to a house. The power plant produces power, AC power, at, let's just say, 25,000 volts. It's a fairly typical value. Now a step-up transformer takes that 25,000 volts and raises it to 500,000 volts. So we know that the ratio N2 over N1 is 20, because 20 times 25 kilovolts is going to be 500 kilovolts. So apparently this step-up transformer has a ratio N2 over N1 equal to 20. Now that 500,000 volts is transported across the countryside to a step-down transformer, which is local to the neighborhood or the area. That step-down transformer takes that 500,000 volts and lowers it to about 7,200 volts. So the lines that you see along the road between telephone poles is approximately 7,200 volts. At the house, the last thing that happens before that line is run to the house is that there's a second step-down transformer right here, which takes that 7,200 volts and lowers it down to 120 volts. Now in doing so, we've taken 25,000 volts, we've raised it to a very high voltage, 500,000, which means we've really lowered the current by a factor of 20. And then we take that 500,000 volts and lower it ultimately back down to 120 volts, which is what the house is going to use. Because that 120 volts is so much lower than the original power, that means that the current is going to be up by that same factor. So we receive power at our home of about 120 volts with relatively high current. Now, why do we transmit the voltage at such high? Why do we transmit the power at such high voltage? Well, we've seen how high voltage means smaller current. If I raise the voltage up from one source to another via a step-up transformer, I've also reduced the current by the same factor. If I've raised the voltage by 20 times, I've lowered the current by 20 times. Now remember, the power loss in a device is equal to I squared R. Whatever resistance there is in the line, and these lines have resistance, the loss is going to be the current squared times the resistance of that line. Therefore, if I can step up the voltage and therefore step down the current, I have lowered the power loss in that wire. In the case of going from 25 to 500,000 volts, I've raised the voltage by 20, I've lowered the current by 20. That means I've lowered the power loss by 20 squared, or 400. So I've lowered the power loss in transmitting that power across those lines by a factor of approximately 400 by raising the voltage to such a high value. That means that we can transport power across long distances with minimum power loss by using very high voltage. By the time it gets to the house, the current that's available is really quite high because the voltage has been dropped down to a value that's common to homes, about 120 volts. And you can also see why we use AC rather than DC, because AC allows us to step up the voltage to these high values. It would be a very complicated procedure to raise DC voltage to such a high value, and even then there are reasons why it's less efficient being transported over long distances. So transformers are used primarily in the power industry to transport power from the power plant to the house in a most efficient way, a way that reduces the power loss for that transport.